Hello, thank you for tuning on. We're going to be talking about some rocket science today, more specifically the derivation and an explanation of one of the most important equations in rocket science, aptly named the ideal rocket equation. But before we go into the proof, I'm just going to cover some of the state variables that we're going to talk about. So I have a rocket here on the right. One of the most important variables, obviously, is the velocity of the rocket moving forward. We're going to call that VR. There's the mass of the rocket, which the mass of the rocket is actually going to be changing, which we're going to talk about in a moment. There's the velocity of the exhaust. That's the velocity at which flying hot gas particles leave the rocket. And then those gas particles have a mass. We're removing mass from the rocket, and the amount of mass we're removing we're going to call dm. So the way we're going to go about deriving the rocket equation is through momentum. So this is going to be an oversimplification, kind of a way to explain how rockets work from a momentum standpoint. So we've got two frames, the first one being at t equals 0, time equals 0. So at time equals 0, our rocket is going to have some mass m, and it's going to be traveling forward at some velocity v. After some time has elapsed at t equals delta t, the rocket is going to take a block of exhaust, a block of propellant, and propel it backwards. So this block of mass dm is going to be moving backwards at velocity v exhaust. So the new mass of the rocket is going to be m minus dm, and the new velocity of the rocket is going to be v plus v exhaust. And this works because of conservation of momentum. The system we're looking at is the entire system, the rocket plus the propellant, and this is going to matter in a little bit. So to start the proof, the first thing we're going to look at is Newton's second law as it applies to momentum. So the sum of the forces equals the limit as delta t approaches 0 of final momentum minus initial momentum over delta t. And we're going to define initial momentum as m plus delta m times v, and final momentum as m times v plus delta v plus delta m times v exhaust. And this equation works because of conservation of momentum. So we're going to rearrange this and rewrite it as the difference in momentum equals to m delta v minus v exhaust delta m. Then we can take this and substitute in Newton's second law to get the net force equals m dv dt plus v exhaust dm dt. So the reason the sign here changed is because the mass being removed from the rocket is negative. Delta m is negative, even though m is positive. So because of conservation of momentum, and we're assuming negligible air resistance, there's no external forces. So we can rearrange this to read m dv dt equals negative v exhaust dm dt. Then we can move m to the other side and differentiate with respect, or integrate with respect to time, to get delta v equals negative v exhaust times the integral from m initial, wet mass, to m final, dry mass, of 1 over m dm. And this obviously equals v exhaust times the natural log of wet mass over dry mass. And that's the rocket equation. So what exactly does this mean for a rocket? Well, this is a logarithmic equation, so we can rearrange this to be in the exponent form. And what this tells us is that there's an exponential relationship between your dry mass, the mass of your airframe, and the the delta v, the amount of velocity that you're able to get out of your rocket. Now this delta v, if you're trying to do interplanetary travel or you're trying to go into orbit, this delta v is going to be escape velocity. And if you're trying to hit that delta v, you're going to have to minimize as much as you can your initial velocity and maximize your or minimize your final velocity and maximize the amount of fuel that is in there. So the other thing we get from this equation is that v exhaust is also a big impactor. So the higher your velocity, the velocity of your exhaust is, the faster you're going to be able to go. And we can increase our velocity. One of the ways we can increase it is purely mechanical. So this is a diagram of a nozzle of the rocket. As we have gas particles moving inside the rocket, as they start to burn, they speed up as they get towards the outside, and when they hit this converging point, they hit Mach 1 and then leave at a much higher speed, which is V exhaust. If we want to increase this V exhaust, we can do that actually by increasing the size of the bell and several other mechanical options. The other way we can do it is actually just decreasing the mass of the particles. So there's research into things like hydrogen rockets that have much lighter particles, which will then be able to move much faster. So I hope that was interesting. I hope rocket science is not as scary to you as it was before. If it is, I apologize. And yeah, thanks for coming.